Hello all, in this lecture we're going to be studying vapor pressure, so you'll need table H. Hopefully you can get a copy of that out so that you can follow along as we're working. And I'll discuss boiling, including the real reason why boiling occurs. And that'll lead us into a discussion about what can affect boiling point. There are several factors that scientists can manipulate to make boiling happen faster, slower, etc. What you should start your classwork page with today is this particular homework assignment. It's questions 44 to 50 on page 131. Don't do it yet, we'll do it tomorrow. And here's your aim. What are vapor pressure and boiling point? Down here, copy down these do now questions and we will do them at the beginning of class tomorrow. So let's start with vapor pressure. Vapor pressure is the amount of pressure produced by a vapor. And so it's shown here. If you have a liquid, the liquid particles can vaporize, and as they come up, they might collide with the walls of their container or each other, and that would produce what we call vapor pressure. So the vapor pressure is the pressure exerted by the vapor above a liquid. So the relationship between the number of particles that exist as vapor and the vapor pressure itself, of course, is direct. The more particles you have over here that exist as vapor, the more pressure they would exert as they collide. So let's talk about this one. This is so important, I will use my highlighter. Which would have higher vapor pressure? A liquid with high or low intermolecular forces. All right, I'm going to break this down for you. If a substance has low intermolecular force, there is low attraction holding particles together. And if you have low attraction between particles, you're going to see a lot of particles leave the liquid and enter the vapor state. And the more particles you have in the vapor state, the higher the vapor pressure. Therefore, in short, lower intermolecular forces causes a higher vapor pressure. Okay, consider two liquids, one being polar and the other being non-polar. Which would have the most particles as vapor and why? Check this out. Polar liquids would have higher intermolecular forces of attraction holding them together. And a situation like this is going to give you more particles existing as a liquid state and less particles existing as vapor state. And the less particles you have in the vapor state, the lower the vapor pressure will be. So which would have the most particles as vapor? That's going to be the non-polar, because the polar substance is going to have less particles as vapor. Now similarly, the one that has the most particles as vapor, the non-polar substance, so most particles as vapor, non-polar, that's going to also be the most vapor pressure, because the more particles, the more pressure. Alright, so I have a video to include here for you for the following, where it says isopropyl alcohol is nonpolar and flammable, so we know its vapor pressure is going to be higher vapor pressure up here. What should happen when I hold a flame to it? If it's both high pressure and flammable, what would you predict would happen? I don't want to leave you in suspense. I'll try to do this demo for you tomorrow, but here's a video showing just what I mean.
Hi again, folks. I'm Chief Meteorologist Jay Burschback at the Imagination Station, along with Carl Nelson. Glasses on for safety today because we are dealing with fire and flames. This is what we've called the whoosh jug, dealing with flammable vapors.
Exactly.
All right, take it away, Carl.
So we've got a 5-gallon jug, water jug. It's completely dry and empty. We're going to add to it a little bit of ethyl alcohol. Okay. Now this is 95% ethyl alcohol, so it is very, very concentrated, if you will.
All right.
It's also very flammable. Jay, what I'd like you to do is pick that jug up and sort of swoosh that liquid around. So what we want to do is generate some vapors inside the jug, and if you can, carefully tip it almost on its side and rotate it. But don't let any of the liquid come out. That's perfect.
Sure.
We want to coat the inside. We're going to build up lots of vapor because that's what we want to ignite. We're going to show you how flammable some vapors can actually be. So tip it totally upright. A little bit of liquid comes out. Let it drip for a second. Perfect. Go ahead and upright it. We'll take this away. And now we've got a very flammable mixture of gas inside there. I'm going to give you some matches.
Okay.
You've got a pair of tongs for safety. Okay, so let's light the matches here. And once you get them lit, give them a second. And then you have you come over the top of the jug and just drop the matches into that flammable mixture of gases.
Right, here we go. 3, 2, 1.
Yeah. It ignited. You get that whoosh of air coming out. That's what we call the whoosh jug.
Yes, yes.
And then the air expands and some of it gets pulled back in. And then there was a secondary sort of whoosh
Yes, yeah.
as it sort of oscillated back and forth.
Okay.
Now, the other thing that happened there that's kind of subtle, we're going to do it one more time, is that when the combustion happens, the gases inside warm up and they expand. And that's
Sure.
what caused that jet of flame to come shooting out. Now, the question is, what would happen if you could contain those gases inside the jug while they cool? Okay, so we're gonna do the same thing again. Jay, I'm gonna let you go ahead and grab your tongs. We'll do the same deal. And this time we'll add a little twist at the end. So I'll let you go ahead and put your matches in there. We're gonna get them lit. And then we'll drop these into our flammable mixture.
Same way.
Let them burn for a couple seconds here. And okay, I think we're ready. Go ahead and drop it in.
There we go. 3, 2, 1.
Okay, we've got some nice oscillation there. And now if we cap this,
Wow.
as that air begins to cool, it takes up less space, and you can see that slight imbalance in air pressure is allowing atmospheric pressure, 14.7 pounds per square inch, to start to crush the jug. You might even see something similar to this if you rinse out your milk jugs before you recycle and put the cap back on. Warm water will do the same sort of thing. No flames involved, so it's a nice, safe way you could do this at home. But isn't that amazing? A little bit of warm air.
Wow.
Let the pressure back in, it pops right back.
Amazing.
Check this out. We're starting to get a cloud formation inside the jug. As we drop the
Love it.
pressure, we got some particulate matter in there from the burning fuel. Cloud in the bottle as well. It's like a bonus.
Lovely.
Don't try this at home.
Sure.
Okay, it is quite dangerous, as you saw from your reaction
Yeah.
when that first whoosh came out.
And it was a whoosh.
It was?
Now we know why it's called the whoosh. All right, wonderful experiment. Thank you.
That was cool, right? Okay, so that means that what would happen is that the alcohol vapors were flammable, and that buildup of vapor pressure caused a jet of flame. All right, table H. Go ahead and get your reference table H out. It'll be a lot easier to read than seeing it on this video. Firstly, which of the liquids represented on this graph is least polar and why? The answer would be propanone. The reason I can say that for sure is that the least polar liquid should produce the highest vapor pressure. And if you're checking out the line for propanone, it has the highest vapor pressure at any temperature. For instance, if you go to 25 Celsius, the highest vapor pressure is propanone. If you go to 50 Celsius, the highest vapor pressure is propanone. If you go to 75 Celsius, the highest vapor pressure is propanone. So that's how I know the least polar gas is propanone. But in general, and this is true for all of the gases you see here, propanone, ethanol, water, and ethanoic acid, the relationship between temperature and vapor pressure is direct. As the temperature increases, the vapor pressures increase. But there is still one mysterious part to this graph that has not been explained, and it's this line. This dotted line at 101.3 kilopascals, which is on your reference table, listed as the standard pressure on table A. So I'll just copy that in down here. And I should add that the vapor pressures will cross this dotted line at different temperatures. But for water, when we follow the water line up, here's water. So when I follow the water line up to see where it crosses the dotted line, it's right here. I'll put a dot there. And then if I follow that down to the temperature line, I'm getting 100. So it's crossing the line at 100 degrees Celsius. So this is not a coincidence. This is also the boiling point for water. So what event occurs as the vapor pressure of a liquid equals the pressure of the atmosphere pressing down on it? Boiling. I highlighted this because it's a really important thing to take away from this lesson. So basically, here's the way I envision this. The atmosphere is pressing down on the surface of a liquid, and the vapor pressure is pressing up against the atmosphere. So here's the diagram I would use to explain this. We have our atmosphere up here, some birds, the sun, and the part of the atmosphere that's going to be exerting pressure on a liquid is going to be the column of air directly above it. So this is that column of air above my liquid. It's pressing down on the liquid, but the vapor above the liquid also exerts its own pressure. That's the vapor pressure, which is pressing up. Boiling will only occur when these vapor pressures can equal or exceed the atmospheric pressure. So there you have it. When the vapor pressure is larger than the atmospheric pressure, you will get boiling occur. There is one extra little thing I'd add in here, which is that in mountain towns, like on the top of a mountain, you actually will get water to boil at an even lower temperature than 100 degrees Celsius. Like where I'm from, water boils at around 97. The reason for that can be understood from Table H. So let's go to 97 on Table H, which is going to be about here. Follow it up until you intersect water, and then see what water's vapor pressure is at that temperature. So I'll go all the way over on the x-axis, and I may be just a little bit off, but it looks like the vapor pressure is going to be around, I don't know, maybe 93 or 94 kilopascals. And we know that water will only boil when the vapor pressure is larger than the atmospheric pressure. So I know that the atmospheric pressure in this mountain town must be less than 94 kilopascals. So that would only be possible if there's less atmosphere to produce less atmospheric pressure. And if you're on top of a mountain, check this out. Well, on top of a mountain, you certainly have less atmosphere above you than if you were at the bottom of a mountain. You have this much less atmosphere. So you would have lower pressure at the top of a mountain, which would mean that water could boil at a lower temperature. All right, let's watch a couple of quick video clips of boiling. So I think what both of those videos showed very well is that boiling is really what happens when the liquid in any point in the liquid area, that you can form a gaseous bubble at any point in the liquid area. So that's the definition of boiling. But as the temperature of a liquid rises, this is all cause and effect right here, but as the temperature of a liquid rises, vapor pressure increases. Eventually, the vapor pressure becomes equal to the atmospheric pressure. When the liquid's vapor pressure equals the atmospheric pressure above it, any particle in the liquid is free to vaporize. This is what we would call boiling. When a bubble can occur at any point in the liquid, the process is called boiling. And the normal boiling point of a liquid is the temperature at which the vapor pressure of a liquid equals 101.3 kilopascals, which is standard pressure. Equivalent pressures to this pressure of 101.3 would be 1 atmosphere, which is also on Table A. And additionally, other equivalent pressures are 760 millimeters mercury and 760 torr. All right, let's do a little bit more cause and effect. This is broken into the things that matter the most for the factors that affect boiling point. The first thing that we'll discuss is the nature of the substance, whether it's polar or non-polar. The second thing we'll discuss is the temperature of the substance and how that affects vapor pressure. And the next thing we'll discuss is the pressure on the substance, which is the effect that the atmosphere has. So starting with the nature of the substance. If the substance is polar, its intermolecular forces of attraction are, of course, high, which means that it won't have many particles as vapor. They'll mostly be liquid, so its vapor pressure would be low. And it's asking about boiling point. Now, boiling only occurs when the vapor pressure equals the atmospheric pressure. And if your vapor pressure is quite low, it's going to take you a while to get it to be high. That means its boiling point would be high. Let's examine the effect of temperature on the substance. If the particles in the substance have a high average kinetic energy, which is a high temperature, the vapor pressure will be high. When the vapor pressure equals the standard atmospheric pressure, the substance will boil. So the higher the temperature, the more likely you are to boil. Lastly, let's examine the effect of pressure on the substance by the atmosphere. At sea level, where New York City is, the atmospheric pressure is standard. That is 101 0.3 kilopascals or 1 atmosphere. Both of these values are from table A. But you should know that at high elevations, the atmospheric pressure is less than 101.3. Therefore, the boiling point decreases as elevation increases. And with that, we've reached our pair up. I would ask you to either sketch this example of table H or rely on having your reference table in class tomorrow, but definitely copy down these questions without answering them. And then we'll do these summary questions in class tomorrow as well. I hope that you understood this lesson. This was our last lesson in Unit 8. Next, we're going to be doing a review to get ready for the test. So thanks for watching and have a great night.